Welcome back everyone, and today we're going to be doing the uniqueness of limits and we'll be proving this. So firstly, let's just start off with a basic notational thing. So previously we have written an tends to L as n tends to infinity. Now this is all well and good and this is correct, but there's a slightly more compact form we can write for an to converge to L, and this is to say, in this case, L is the limit as n tends to infinity of an. And so we can write this to say that an converges to L as n tends to infinity. What we want to do though is use the epsilon delta definition of a limit to actually prove that this L should be unique if it is the limit of an. So as for the proof that L is unique, let's suppose it's not, and we'll derive a contradiction, or in fact we can sort of assume there are two different limits and we'll just show they're equal. So let's have an tends to L1 and an tends to L2. Now I'm just going to omit the n tending to infinity, but that is implied here. This is as n tends to infinity. So here we want to use the epsilon delta definition. So what does this mean? Well, this means that for every epsilon greater than 0, and this will be fixed now, we'll only write this part once, so epsilon is fixed. So there exists n1 in the naturals such that for every little n greater than or equal to n1 we will have an minus L1 is less than epsilon. Now actually here, because epsilon is arbitrary, we can actually write epsilon over 2, and this will become a bit apparent later, and you'll know this when you've done it before and you've seen this before. But actually this will make things a little bit prettier in the end. But because epsilon was arbitrary, if you gave me a tolerance of a half, I could give you a tolerance of a quarter. Because it converges and it works for any of them, you can always divide epsilon by 2. So here this is true. Similarly for this fixed epsilon, there should also be an n2 in the naturals such that for any n greater than n2 we'll have an minus L2 is less than, again, epsilon over 2. And we can just choose that half just for argument's sake, but it's true whether you use epsilon over 2 or epsilon over 1000 or pi epsilon, whichever you please. What we have here now is that if n is greater than n1, this will hold, and if n is greater than n2, this will hold. So actually we can take little n to be greater than the maximum of n1 and n2, and then both of these hold. So if n is greater than or equal to the max of n1 and n2, then, and here we're going to use the triangle inequality. So if we consider L1 minus L2, what we're going to do is we're going to sort of add 0 in this absolute sign. So here, this will be L1 minus an, and then minus, in brackets, L2 minus an. Here, what we've done is we've minus an an, and we've plussed an an. So actually, these are the same thing. But now we can use the triangle inequality, and this is L1 minus an plus L2 minus an, and because n is greater than n1 and n2, both of these statements here hold. So L1 minus an is less than epsilon over 2, and L2 minus an is less than epsilon over 2. And so if we now read this, what we have is that L1 minus L2, the absolute value of their difference, is less than epsilon, and that was for any epsilon greater than 0 you pick. So for any tolerance you can give me, I can tell you that L1 and L2 are that close together, and since they were sort of picked in advance of epsilon, that tells us they must be the same number. This actually rides on a small assumption that there are no infinitesimals in the reals, but this is a side lemma, and you can either look it up online, or if there's any request I will make a video on why there's no infinitesimals in the reals. But given that, this therefore implies that L1 must be L2, and so our limit was unique, and we're done. Thanks for watching.